So hello and welcome everyone. My name is Guhan Thope and I'll be coordinating today's afternoon session. So this session is titled Learning and Modeling. It will include 4 talks, each of 20 minutes, followed by a 2-minute discussion and a 2-minute question answer session. The first talk the first talk is titled Learning from Low-Rank Tensor Data, a Random Tensor Theory Perspective. The speaker for this talk is Mohamed Amine Seddik.
Hi, everyone. I am Mohamed Amine Seddik from the Technology Innovation Institute in Abu Dhabi. And I will be presenting this work today, who was done by me and my co-authors from Huawei and in Riyadh in France. So I had other slides that are moving. It's fine. I had other slides that are with pauses, but you had that too, which is fine. Problem. The presentation will be about like a learning problem where we suppose that we have data that are like a simple set in which are just 2 classes where the means are low-rank tensor, low-rank tensors. And this example is a rank 1 tensor. So we have data that come in from first class, which are minus m plus zi and plus m plus zi for the second class, where the m is a tensor of rank 1. So it's the product, like the outer product of k many vectors. And in particular, if you take k equal to 1, you get this simple setting that we have in machining of the mixture of 2 Gaussians. And even for if you take k equal to greater than 2, a standard approach would consist in flattening your data into some very big vector and then do the classification with this data. So the question that we are asking here is, can we build some optimal classifier which can give us better accuracy than just flattening, like seeing the data that we have as vectors. So how can we use this Lorentz structure in the data in order to get an optimal classifier? And can we characterize also the theoretical misclassification error that we can get for this classifier? And like basically compute the gap between the flattening operation and using the Lorentz structure. So I have 2 settings here in this presentation. The first one is in supervised learning setting, the second one in unsupervised learning. So in the supervised, we assume that we are given a data tensor which consists of an n IID tensors, which are each one is of dimension p1 to pk, and we have corresponding labels -1 and 1. And we denote also here like this matrix X, which will be just the flattening along the it's a reshaping of the initial tensor. I want you to keep in mind these 2 notations. So big P is the product of all the dimensions, and small p here is the sum of the dimensions. So these 2 quantities will be playing an important role in the analysis. So we consider a simple rich classifier with some parameter that is very big compared to the spectral norm of this covariance matrix. And we end up like this is just a matched filter classifier. So you basically just project your data onto the vector of labels, and it gives you the weight vector, which helps you decide once you do the inner product between this weight tensor and a new data point, and you take the sign, it gives you the classifier decision function. Okay, so in the following, we'll be working the assumption that the dimensions of this tensor are basically of the same order as the number of samples that we have. And we suppose that this m, the norm of m, is being of order 1. So meaning that when we increase the dimension or the number of data points, the classification problem stays reasonable to do. Like it doesn't get very complicated or impossible to resolve. Yeah. Okay, so the first result, which is the very basic result, considers the fact when the classifier when we flatten the data. So it's just a ridge classification problem. So we have so if you basically just compute W inner product with some its I tilde, like a new test point, you get that it's basically a mixture of two Gaussian random variables. The decision function is a mixture of two Gaussian random variables. And we can compute the classification error using like the Gaussian tail function like this. And in here we see that like the error will depend on two parameters, basically this means, and this variance, which depends on the ratio big P over small p. And in the regime that we considered is if the dimensions grow to infinity or the number of samples, then this variance will explode basically. So yeah, because the product of the dimensions will get much higher than the sum of the dimensions. And now we consider the case where we use this Lorentz structure in the data. So basically, if you go back to the tensor W here, like it's just a production of the contraction of the tensor, like the data tensor onto the labels, it can be expressed as following. So we have a rank 1 terms, which corresponds to the signal or the mean into our data points, and a noise term, which is given by this tensor here. And by the way, in the beginning, I assumed that the entries of the noise term are Gaussian, but we can relax this assumption since we have just here a sum of IID random variables basically for each entry. So we can relax that assumption as well. And in this case, we define the tensor ridge regression like a classifier as follows. So instead of taking W directly into the inner product, we replace this W by a best rank 1 approximation of this W. So we perform a best rank 1 approximation as follows. So basically, this best rank 1 approximation will be an estimate of the rank 1 term in W. And we have basically a denoising process where we like forget about this noise, try to reduce this noise here. So our classifier here is just like now the product between this rank 1 approximation and a new data point. One remark is that computing this best rank 1 approximation, tensor rank 1 approximation, is in general an NP hard problem, but we can still get some reasonable like estimate if under some condition. Basically here, if the norm of this M, like the distance between the two classes is larger than this ratio here. I put in the paper all the references corresponding to this situations. So basically, when we look at this tensor, the weight tensor, it will be what we call a spiked tensor model. So it's a model of the form where we have a rank 1 tensor plus noise tensor with IID entries. And so actually this paper, like this work here is heavily based on a paper that I did before, like a bit before, which was accepted lately at Annals of Applied Probability, which basically studies this rank 1 like spiked tensor model. And in this result, what we gave exactly is that as the dimension goes to infinity, like the spectral norm corresponding to the best rank 1 approximation basically will converge to some quantity almost surely, and the alignments between the estimates, so the UIs here and the HIs, so the cosine similarity basically will converge to this some quantity qi of this lambda bar, where these quantities here are defined through some fixed point equation. And this result, like if you want to have like a look into the paper in more details, it uses some arguments from random matrix theory to derive these equations. So basically this GZ that we see here corresponds to the spectral measure of some random matrix which is related to the tensor under study here. Okay. So yeah, coming back to the tensor rate regression classifier, having this result, we can now characterize this misclassification error in terms of the different quantities involved. And we see that basically it depends only on the norm of M and the ratio between P and N, and there is no ratio like big P over small p. So meaning that when the increase now the dimension of the data, the variance stays constant basically. So we don't have this phenomenon where the variance explodes with the dimension. And of course, when we compare now the misclassification error between an approach where we flatten the data into vectors and when we use this tensor approach, we get a better misclassification error, so a smaller misclassification error in this case. And like the dots here correspond to what we do, so simulations, and the curves correspond to the theoretical performance. And here in the dashed green lines, it corresponds to the classifier where we perfectly know about the means. So if we give us the mean, then we have this classification, and we see that the tensor approach is almost close to the optimal classifier basically. And in both columns, if we increase the number of samples, then the flattening basically gets closer to the tensor of the optimal classification. In other words, if we have like a limited number of samples, then taking into account this tensor structure will give us better accuracy basically. This is just a phase thread like diagram where we show that this is rich classifier performance in terms of P over N, ratio P over N. And when we vary the norm of M, basically the distance between the clusters, and we see that like there is a huge difference between the tensor and the flattening operation. But in practice, we don't have the curve here. We have something slightly different, which comes from the fact that resolving the bit rank representation is NP hard in practice, but still in practice we can get some accuracy which is better than the flattening operation. Okay. And the same here in the last part. So we have the setting of unsupervised clustering problem. So again, if we assume that we don't have access to labels and we apply just a linear clustering approach where we reshape the data tensor into some huge matrix and apply spectral methods. And the tensor approach would consist in performing bit rank approximation in this case. So here again, we see that the performance of the linear clustering will depend on this BP, which is the product of the dimensions, and which makes like the classification accuracy poor as the dimension grows to infinity over. And while in the tensor case, we don't have like this big P effect appearing in theory. So yeah, again, when we apply the linear, so we get basically a higher variance in the data, while when we apply the tensor-based method, we get like a smaller variance, which gives us better accuracy, basically. And the thing is that these tools now can characterize exactly what is the theoretical accuracy that we can get from this data model. Specifically, we have this diagram here, which shows misclassification error for both approaches in terms of the distance between the clusters, and we see that basically at some point we can retrieve like the signal from our data in polynomial time here. So it's a region where it's possible to recover the signal, and there is some region where it's NP-hard. Yeah, almost. So it's NP-hard, and below some threshold, it's impossible to recover the signal, basically. So yeah, I think that's it for me. Thank you for your attention.
So we will now have a 2-minute discussion session.
Yeah, thanks for the nice talk. I just wanted to, maybe highlight one takeaway I had from reading this paper. Okay, so before I mention that very concisely, I just want to define this term called Tensor PCA. So that exact version written there is, inspired by some earlier works, but the basic idea is this. So let's say that you're given a tensor, which looks like a rank 1 spike, like some lambda constant times a tensor product of a bunch of tensors U1 to UK, plus some Gaussian noise. Okay, the task is to recover this so-called principal component from just A. Okay, and this is called the spike tensor model, or like I think it was introduced. It's also called Tensor PCA by Richard and Montanari. So this problem is called Tensor PCA, and you can think of it as a generalization of just like PCA, principal component analysis. So the main takeaway I wanted to mention is from reading this work, it seems like pre-processing the tensor data using Tensor PCA does give you like performance improvement, both like empirically and theoretically. So in some sense, I mean, they don't do it for the data that's given to you. That sometimes they do it on like some sort of information you get from the data, but basically like, denoising the data and using what you learn from this top principal component does help you like, improve in performance. So this to me is like a very nice insight I got from the paper. So I just wanted to mention like a few things that I thought of when I was reading this. So yeah, one question that was raised was like in some regions it's NP hard. In those regions, can we like use sub-exponential algorithms as opposed to like polynomial time algorithms? So some works have done this for Tensor PCA, and I can imagine like something similar like working in this regime. The next question I want to ask is, I felt like most of the technical difficulty came because of analyzing like asymmetric tensors instead of symmetric tensors. And in some, some other works on like, Tensor PCA and for lower bounds, people have realized that these two are actually like not too different from each other. And they found ways to like go between one and the other. So it would be nice if like all the hard work works for both like symmetric and asymmetric tensors. Thanks.
Thank you for the very nice questions. I will try to answer maybe the first one, but for the second one, I don't have like any clue exactly how we can approach the problem. But concerning the first one, so what's known for that for now in the literature basically is that we have this NP-hard regime where there is no polynomial, like all the polynomial time algorithms that we know so far do not like converge in this region. But actually, it's just a matter of initialization. Like if you apply this tensor power iteration algorithm and you find some proper initialization that gives you some slight minimum correlation with the signal, then you can get some good estimates here. And in fact, if you keep repeating this tensor power iteration with many initialization, random initialization, then you can get something which gives you some good estimates in this region, basically. So yeah, of course we can basically use sub-exponential time algorithms to have some good initialization and then improve the estimation based on this. For the second question, I'm sorry, but we can discuss later maybe. Thank you.
So do we have any questions from the audience here? Do you have any questions from the online participants? Yeah, please go ahead.
Do you think the analysis could carry over for other kind of losses than the ridge loss, since for classification it doesn't seem like the most appropriate one?
For what? Sorry.
Do you think that your analysis could carry over to other losses than the ridge one, actually? Because for classification it doesn't seem like the most appropriate one. But...
Okay. So here, like if we rewrite like this classifier in terms of tensor notation, it's minimizing this problem under the constraint that the weight is a Lorentz tensor. So I guess it can be generalized to other losses, except that we need to add this constraint in the optimization problem.
Okay.
Yeah.
Okay.
Thank you.
But I mean, you lose the closed form thing. It doesn't matter?
Yeah. Here I just used like, typically it's just a linear projection of the data. But I mean, we need to work it a bit, maybe if we don't have a closed formula, and try to find something.
Yeah, it might be actually harder. Because,
it will be harder, but I think like there is some concentration phenomena which occur that gives you like access to I didn't do it, but I guess it could be doable in some sense.
Yeah, sounds good.
Yeah, thank you.
So let's thank the speaker and Gautam for the discussion.